Welcome back. We're going to do Prim's minimum spanning tree. So what is that? Well, Prim is the author, of course, and what we're trying to do is convert a graph into a tree. And that tree will have the least cost. By minimum, we mean least cost. Least total cost. And spanning means that it uses all the nodes. And tree means it's a tree. So why would you want to do this? Well, let's say you have a house, okay, and you're trying to run wire. So there's one point, the root, where the power comes into your house. And power grids or power distribution circuits in your house are a tree. So what you might do is say you want an outlet here and an outlet here and an outlet here and these different outlets. And you might calculate the cost of the wire runs to all of these different houses. Like maybe it costs you $10 to go this way, maybe it costs you $2 to go this way, and $2 a wire to go this way, and $3 a wire to go that way, and $4 and $6 and $9 and $42 because you got to go down in the basement or something, and $10 and $3 and $7. So this is the graph representing all the possible ways that we could run wires, but all we really need is a tree. So we want the tree with the cheapest total cost, right? Cheapest total cost. So just by inspection, you could see that tree would be this one, this one, this one, and probably, let's see, the 4, I guess, right? So if we just did that, the resulting tree it's this guy with the 2, the 2, and the 3. It's this. So this is the root, and the total cost is what? It's 4 plus 2 plus 2 plus 3. It's $11. Okay, so this is the idea of a minimum spanning tree, because often what we really want in the end is a tree. And so we start off with a graph, and the graph represents all possibilities, but the tree represents the final solution. And the final solution is a tree that has the cheapest total possible cost. So that is the basic idea. The algorithm that we're going to do is Prim's, and it's in the notes. Used to be, at one time it was page 64, but my pages change. But find this minimum spanning tree thing in the notes and look at it. So let's see, have I done everything here? A weighted graph can be converted into a tree, yeah. It's not a binary tree. It's like this guy here has 3 children, this node here, if this were the root. There's many solutions for a given graph, like depending on who you choose the root, right? This one, if I choose this as the root, I get this tree. If I choose this guy over here, I would get a different tree, right? So the choice of the root is one of the variables on here. Let's see. So here's what we need to remember to do Prim's algorithm. We need to remember something called the distance. Now the distance has a particular definition for this one. And this is a sticking point because we're going to do another algorithm that has a different definition of distance. But otherwise the algorithm is similar. So be careful here. So the distance is the smallest distance from the node to the tree. Okay, so we're going to have a tree, and then we're going to have candidates, that is, nodes that are adjacent to the tree, but not in the tree yet. All right, we need to remember that, and I'll talk more about that. And then we need to remember the parent, or who each node's parent is. Yeah, and then we have these things called candidate nodes, which are nodes that are adjacent to the tree, but not yet in the tree. And let's see, a root has no parent. So this is the data structure that we need, that will work, is just an array for all the nodes, and then we remember the distance and the parent. Okay, here's the algorithm. You pick an arbitrary root, so you can start anywhere. I'll give you a root to start at. Then you identify the candidates. Okay, so the candidates are nodes that are, right here's the definition, that's next to the tree, adjacent to the tree, but not yet in the tree. Okay, so you identify the candidates. Then you, in this graph here, you update the distance of all those candidates. And you update the nodes, its parent, the candidate's parent, if it were going to be in the tree, who would its parent be? Then you choose the cheapest. You choose the cheapest candidate. So we call that a greedy algorithm. That is, you're not looking long term. You're just looking at the candidates, the ones that are close by, and you choose the cheapest one. That might not always yield the optimum solution, but most of the time it does. That's the human way of doing things. Not to be, I don't mean disparaging or anything, but a greedy algorithm just looks at the near term, basically, closest stuff, and it usually works. And so humans are kind of, in my opinion, or I don't know, maybe it's science, but humans kind of go that way. If we sort of just look at what's expedient now, and it works most of the time. That works. There are some times when that doesn't work, and our short-term interests are not don't yield the best long-term results. But anyway, that's the idea of a greedy algorithm, and it usually works, but it might not. Okay, so keep that in mind. So you pick the closest guy and add him to the tree, and then if all the distances are 0, you're done. That means everybody's in the tree. Otherwise, you go back to 2, which means you identify a new set of candidates, mark how far they are from the tree, mark who their parent would be, choose the closest one, and you just repeat in that fashion. Okay, so let me work one. So let's say we have a graph that looks like this right here. Just some nodes here, and I'll put some links on here. Just sort of arbitrary weights. So we're going to choose A as the root, and that's arbitrary. So if I choose A as the root, then A is in the tree. So I have a data structure here that I'm keeping track of who's in the tree. It's A, B, C, D, E, F, and I got some extra squares. And I need to keep track of 2 pieces of information: the distance to the tree. So this is the distance of candidate nodes to the tree, and then for each node, who their parent is. So the bottom row is really storing a tree in an array, which is a simple way to store a tree, but for this algorithm, it's good enough. So let's see. We choose this guy. His distance to the tree is 0 because he's in the tree, and his parent is himself, let's say, because he's the root. All right, then you run through the steps of the algorithm here, which I'm going to do. Right, so we picked an arbitrary root to add the tree. Then we identify the candidate nodes. So who are the candidate nodes? The candidate nodes are the nodes that are adjacent to the tree. That's these 2 guys, right? B and C are adjacent to the tree. A is in the tree. I'll circle it to show that it's in the tree. And B and C are adjacent to the tree. So B and C are our candidate nodes. So B is, so the links. B is 2 away from the tree, and C is 3 away from the tree. And their parent, if they were added to the tree, would be A. Okay, so these are, B and C are the candidate nodes. They're adjacent to the tree, right? Oh, D is also a candidate. I left that dude out. So D is a candidate. He's adjacent to the tree. That is, he has an edge. Doesn't mean how far away he is on the paper. It means that there's a link. Okay, so D is adjacent to the tree, a distance of 1 away, and his parent would be A. So B, C, and D are are our candidates. That's hard to say. Okay, so we identified the candidates, we updated their distance to the tree and who their parent would be. And now we're greedy, so we choose the cheapest one, which would be D, right? So put D in the tree, which means his distance goes to 0 because he's in the tree now. All right? And that's the first cycle. So then we go back around, we go to 2. So we identify some new candidates that we got. So D is in the tree, B is adjacent, but F is adjacent now. So that's a new adjacent node, F. Right? So the addition of D to the tree made F a new candidate. Okay, so we just repeat. So we have 3 candidates, B, C, and F. Oh, F, his parent is D, and his parent is D, and his distance from the tree is 1. Forgot to update the table. Okay, so we've got 3 candidates, B, C, and F. B, C, and F. And their distance away from the tree, which is just the link weight. So then we choose the cheapest link, which is this guy. So we add F to the tree, which means his distance goes to 0 because he's in the tree. All right. And then we have a new candidate that shows up. E becomes a candidate because E is now adjacent to the tree via his neighbor F. Okay, so E is a new candidate. He's 1 away from the tree, and his parent would be F. If you added him to the tree, his parent would be F. So we found a new candidate. We updated this information. We cycle back, go to step 2, basically, choose the cheapest guy. So the cheapest guy is this guy. So you add him to the tree. So F is now in the tree. That means his distance goes to 0. And that's the oh, no, we're not done yet. So then we look for more candidates. So you might note that E is now in the tree and he's adjacent to B, but that's worse. E is 4 away from B. That's worse than 2. So we ignore that. We don't update any of these distances. And that's it. That's the only thing that changes. So now the cheapest guy to add is B. So we add B to the tree, which means that his distance goes to 0. And then we look for new candidates, and there's no new candidates. Then we add C to the tree, and his distance goes to 0. And this is our answer. And the total cost is 1 plus 2 plus 3 plus 1 plus 1, whatever that is, 5, 6, 7, 8. Okay, that's the answer. Let me do another one. I'm going to do a brand new one. This one, by the way, is posted already. It's in the notes. It's the exact same problem. But let me do another Prim's example. Prim's example 2. I'll just make up a tree here. A graph. Let's do something with, let's do this guy. Just made him up. A, B, C, D, E, F, G. Brand new tree here. And we'll make this array. So the distance to the tree, the distance of the candidates to the tree, or how far away are the candidates from the tree, and then who is their parent or who will be their parent. All right, so let's just use A again. Once again, I mean, you could build a different tree by choosing a different root, but somewhat arbitrary, but let's just choose A. So A is in the tree. His distance away from the tree is 0 because he's in the tree. And his parent is himself because he's the root. Okay, so who are our candidates? It's hard for me to say that this morning. So B is a candidate, and he's 2 away from the tree, right? 2 away from the tree. It's really just the link weight of the adjacent nodes, the nodes that are adjacent to the tree. And his parent would be A if you added him. And C is adjacent. Ooh, I shouldn't circle this B. Pretend this guy's not circled. And C is 5 away from the tree, and his candidate would be A, his parent would be A. And D is 1 away from the tree, and his parent would be A. And E is 4 away from the tree, and he would be his parent would be A. Okay, so we have these candidates, B, C, D, and E. Right, B, C, D, and E are candidates. And this is how far away they are from the tree: 2, 5, 1, and 4. So who's the cheapest candidate? This guy, right? So that's the greedy part of the algorithm. We always choose what's best right now, and usually that works. But it might not work sometime, right? Like if D had a bunch of neighbors here that were very expensive, way down, further down, then you might get the worst solution by being greedy with D. Anyway, that happens sometimes, but most of the time greedy algorithms work just fine. So we're going to add this guy to the tree, which means his distance from the tree goes to 0 because now he's in the tree. So D is in the tree. Okay, we cycle back because all our distances are not 0 yet. We cycle back to identifying candidates, and the addition of D added a couple of more candidates. It added F is a candidate. F is 3 away from the tree via parent D. And G, this should be a G. G is 2 away from the tree via parent D. And then look to see if any of the other candidates got better. And 1 did, right? This, by the addition of D, C is now closer to the tree by his distance is now 3. So you have to update this C guy here, right? Because C, he was 5 away from the tree. Now he's 3 away from the tree via D. He was 5 away from the tree via A. Now he's 3 away from the tree via D, right? We have a better way to get to the tree, a better way to add C to the tree. What else? E is, with the addition of D, E is 9 away from the tree. That's worse than 4, so we don't update that. Right? 9 is worse than 4, so we don't update that. And let's see, anything else? Excuse me. Oh, I don't even have a link down here. Let's make it 6. Nobody else? No. Okay, so you added D, and then the addition of D added candidates F and G, and it updated candidate C. So then we just choose the cheapest now. So we have 2, 4, 3, and 2. We have 2 2s. So you could choose either one, but in the algorithm we would probably run down through this array and choose the first one probably, or maybe we would choose the last one. Let's choose the first, all right? So let's throw this guy in there and make him 0. So this B becomes part of the tree, so his distance goes to 0, right? And then 7, F, you got to update the candidates after you added B. So 7 is, F is 7 away. That's worse than 3, so we don't update it. And that's the only thing that might have changed. Okay, then we choose the next closest guy, which would be the D, because he's 2 away. So you put D in the tree, his distance goes to 0. G. You put G in the tree, his distance goes to 0. His parent was D. And then you look for updates, and we get one, right? Because now the addition of G added, it made E closer to the tree, right? Right now, or before we added G, E was 4 away from the tree via parent A. Now the addition of G makes E, right, 1 away from the tree via parent G. Right, so you add nodes to the tree, and then you update the candidates. You choose the cheapest one. Add candidates to the tree, update the links, choose the cheapest one, and just keep going around like that. So the cheapest one is now E. It's 1 away from the tree, so you put him in the tree. So his distance from the tree goes to 0, and his parent was G. Then you look around to see if anything got updated, and the addition of E brings D as a potential candidate, but the distance is 9, which is worse than well, D's already in the tree, so yeah, it doesn't get updated because D's already in the tree. You just want to update the candidate distances if they're cheaper, right? Update the candidate distances if they're cheaper. Next cheapest guy to add that's not in the tree is, well, we've got a 3 here, and we've got a 3 here. So we could add C to the tree, or we could add F to the tree, and the algorithm, let's just say it chooses the first one. It just depends on how you write the scanning algorithm that chooses these guys. But let's just say you're going to choose the first one, so 0. So this guy goes into the tree, his distance becomes 0, he's in the tree, and then you look for candidates. As F gets better, right? The addition of C makes a better way to get to F. So you update this 3. So F, right, used to be 3 away from the tree via D, but now it's 2 away from the tree via C. So this becomes a 2, and this is a C. And then you scan for the cheapest guy, which, excluding the zeros, of course, and 2 is the cheapest. And so you throw him in the tree. This is the resulting tree, and the total cost is the total cost is 2 plus 1 plus 3 plus 2 plus 2 plus 1, right? 2, 1, 3, 2, 2, 1, whatever that is. And this is the resulting tree, which you could redraw if you wanted to be like, pretty about it. Yeah, this is the total. This is the tree, the minimum spanning tree. It's given this graph, this is the tree that covers the graph. That is, it uses every node, but it has the cheapest total link cost, right?